Hey, good afternoon, everybody. It's a great pleasure. It's a real treat to welcome Emmanuel Candès to today's colloquium talk. Let me tell you a little bit about the Institute, and then I'll get out of the way and introduce Emmanuel to give the talk. So the Digital Transformation Institute, C3.ai's Digital Transformation Institute, is really to think about how the confluence of cloud computing, AI, machine learning, Internet of Things is really transforming how we do business, how we do government, and how we think about society and social networks. In fact, not a day goes by now when I hear this in boardrooms and academia. There's people thinking about having tracks in their bachelor's offerings on digital transformation. So we're really very pleased that if there's any sort of silver lining in COVID, it's that it has accelerated digital transformation. So the Digital Transformation Institute is funded by C3.ai and Microsoft. And, it's co-led by Berkeley and Illinois. My buddy Shrikant is the co-director of the Institute. It includes Carnegie Mellon, MIT, Princeton, Chicago, Stanford. I got Carnegie Mellon and the Lawrence Berkeley Labs, as well as the National Center for Supercomputing Applications at the University of Illinois. And, we've been going most of the summer and the fall, and this is just to give you a sense of the remaining talks for the fall semester. Zvi Joseph from Carnegie Mellon will talk about reconstructing the SARS-CoV-2 response pathways. René Vidal, who is actually a co-conspirator of a lot of us here on the mathematics of deep learning. You may know that René and Yi had a really blockbuster workshop last week at C3DTI on the analytics of deep learning. Nancy Amato will talk about, it's a long title, but really about computational biology and its applications to SARS, MERS, and of course the coronavirus. Stefana Parasco and Corina Tarnita from Princeton will talk about, they're both architects, and they'll talk about what architects think about being able to do social distancing. And finally, Karen Chappell from Berkeley will talk about really a hot topic about how COVID is really exacerbating social inequalities, actually inequalities in housing and possible evictions and so on and so forth. And that's on December 10th. It's a joint project with Princeton. Okay, the format of this talk is 40 minutes presentation, 15 minutes Q&A. Please use the Q&A feature to ask questions. Camille will be moderating it, and she'll also be available on to upvote and help you as time goes on, and we'll try to answer as many questions as we can. Okay, so today's speaker is going to talk about really some wonderful, exciting work. I think Emmanuel is just a star. Oh, sorry, I meant to read the title before I moved over here. Reliable predictions, counterfactual predictions, equitable treatment, and predictive inference. And it's so exciting because, so much in machine learning is really about correlation, but really a focus of today's talk is about causation and how you bring causation into the story. And I can only begin to tell you how fantastically important this is. A little bit about Emmanuel. Emmanuel is really one of the world's leading authorities. He's a chair. He holds the Barnum-Simons Chair in Math and Stat at Stanford, and also in electrical engineering. He's recently been named the co-director of a new data science institute at Stanford, which is an exciting new announcement that Stanford made. Before he came to Stanford, he was a professor at Caltech, and his interests are very, very broad: computational harmonic analysis, statistics, information theory, mathematical optimization, scientific computing, inverse problems. We've had the pleasure to work with him on aspects of principal component analysis. I can only tell you how wonderful it is to know Emmanuel's sort of really encyclopedic reach over God knows how many fields. He has given a huge number of plenary lectures, and he was just telling us, well, he was recently recognized for his science by the King of Spain in Asturias, and he was telling us about the travails of getting there for traveling at this time. He is a member of the National Academy of Sciences, a Waterman Award winner, and American Academy of Arts and Sciences. He was elected to both in 2014. So without further ado, I will turn off my screen share, Emmanuel, and I will turn it over to you. I think I have turned off the screen share. You should be able to take it on, Emmanuel.
Yeah. Thank you very much, Shankar, for the wonderful introduction. Can you hear me okay?
Yep, we hear you perfectly, and I'm going to turn my video off too.
And also, congratulations on starting this wonderful DTI and for the success you've had so far. So as you said, we're going to talk about predictive inference and some recent progress in predictive inference. And if time allows, I would like to talk about counterfactual predictions. So just to not waste any time, this is machine learning 15 years ago. The hot topic was to, of course, predict movie ratings. And I think you and I, we can agree as to whether or not we got these predictions right or wrong did not really matter. They're inconsequential. But if we fast forward to today, we use machine learning tools in extremely sensitive applications. For example, federal agencies use machine learning for facial recognition. You're probably aware that criminal risk assessment scores are used and widely used by courts in the United States to make incarceration and sentencing decisions by judges. And frankly, it is hard to think about any application that would be more critical than this. And so we're far from just seeing how much I'm going to like a movie. You know that lots of companies are using machine learning to recruit new employees, but also to promote employees and individuals. And of course, there's a promise, which is, I'm sure, what you study in your institute, that data, machine learning, AI will not only improve business, but will improve science itself. And so the stakes are very, very high. And so the stakes are high, and they're even higher when we consider that when we deal with individuals, we have an obligation to be as equitable as we can. And I'm sure you're all familiar with the ProPublica story that broke out about 4 years ago that showed that, you know, if we were to look at defendant with a high risk scores of recidivism, there was a huge discrepancy between African-American defendant and white defendant. So we need to be extremely careful about the way we use these machine learning tools to impact people's lives. So really what we want to talk about in this lecture is we want to use data. We want to use data to improve science, to improve business, to improve society. And I think the main question we want to talk about in this lecture is how much have we really learned from the experience of others? If the promise of data science and AI is to use data about others to inform decisions, how much have we learned from the experience of others? That's one. And connected to what I just mentioned about a very minimalist view of fairness, as you'll see later in the talk, how do we communicate what we've learned without hurting people, right? Without discriminating against people. So we're going to talk about this. And I guess that the main framework we're going to think about during this lecture is, well, we're now using AI and machine learning and in very sensitive applications. And so we're going to make predictions, and these predictions will lead to actions, and the cost of the wrong action might be extremely high. So just to think a little bit about a concrete example, we might think that, you know, applicants, we have a college receiving applications of lots of high school students, and maybe a college is interested in predicting the future performance of applicants. And so we can imagine that we have a quantitative GPA that we want to predict after X years in college, let's say at UC Berkeley. And we're going to have a predictive engine that will spit out a number saying, well, for this applicant, given the characteristics that I could measure, I predict that their GPA is 3.62. And this, of course, will have consequences in terms of admissions. But as I try to argue, these decisions are extremely important, they're extremely consequential, so we need reliable systems. In particular, here's what we're going to try to argue about in this lecture. We would like to have a confidence in what we actually give to an admission officer to inform his or her decision. And so the kind of things we're going to focus on are what we're going to call prediction intervals. So we're going to review prediction intervals in a bit, but what we want to do is we want to create, to be able to predict a range of values for the outcome we're trying to predict, such that the outcome falls within range 90% of the time, right? And so this is extremely important. Instead of just reporting an estimate or a guess of what Y might be, the response of interest might be, I'm going to ask you to predict a range. But the prescription here is that you better be right 90% of the time or 95% of the time. That is, you must be within range 95% of the time because the cost of the wrong action is so high. And so one question is, why don't we see this very often, right? Why don't I see prediction intervals very often? And I think one explanation is that because nowadays we use extremely sophisticated predictive engines, we're way past beyond simple regressions. And so it's very unclear how I might actually construct these predictive intervals. And so yet, my point is that I want to use these models to make predictions, but I want to add a protective layer on top of it so that I can actually trust what these very sophisticated predictive engines tend to produce. So this is going to be the subject of this lecture. And so the first part of this lecture, we're going to see how it's possible to add such a protective layer so that you can produce outcomes you can trust. And I've just learned, and that's kind of something I'm excited about, that the method you're going to use actually is a key building block in the method that the Washington Post will actually use on election night to forecast election results as the night goes on. And this is thanks to the wonderful work of John Cherian and Lenny Bronner. So let's see a little bit about the kind of ideas that the Washington Post will actually use on election night. So just to formalize things a little bit, we want to focus on prediction intervals. And so just as is common in machine learning, we're going to have training data, and we have attributes, features X, and a response Y. And so in my previous example, the features might be the high school identifier of an applicant, her high school GPA, her ACT scores, a level of physical fitness outside extracurricular activities, and so on. And Y is a measure, a quantitative measure, let's say, of how we think this person will do in college. And again, we want to learn from the experience of others to be able to make a good prediction. And instead of just reporting a prediction, what we want to do here is we want to report a prediction interval, that is, an interval which is constructed based on previous data in such a way that for new applicants, the predicted range contains a true label 90% of the time or 95% of the time, or this is however you want to fix it. But the prescription we have is that you need to give me a range that contains a true label 95% of the time. And this has to hold no matter what the distribution is and no matter what the sample size is. And so in plain English, we want to be able to say something like this. We want to be able to say that based on the candidate's high school identifier and her GPA and her ACT scores, and anything you can have measured, I'm going to predict that the college GPA after 2 years, let's say, will fall in the 3.4, 3.8 range. And when I make this prediction, I'm correct 95% of the time. That's a prescription. So how are we going to do this? Well, if I have data, and if I knew actually the distribution of the data, that I know it actually is a joint distribution of the features and the response y, then I would know the kind of the conditional distribution of y given x. And for each value of the feature, for each value of the feature, I would have a conditional response, a conditional value of a distribution for the value of y given x. And because this is known in the case where, of course, if I know the whole data generating mechanism, then I would be actually able to actually calculate the quantiles of this distribution. For each value of x, I can calculate the 5th percentile, I can calculate the 95th percentile for each value of x. And of course, I can join them like this, and I would know exactly how to give you a prediction interval for a person with a new x. I would just return, someone shows up with a new x, I return this range. But obviously, if you knew the distribution, there would be no machine learning problem to solve. And so all you've got is you've got a sample. And what we want now is we actually, on data alone, produce a prediction interval such that on future test points, you're correct 90 or 95% of the time, when what you see is just this. So we're going to see some technology that achieves this. And it's a bit surprising at first that you can do it, but I'll show you some technologies that can achieve this. And this is going to be based on two ideas. The first is the idea of quantile regression, which is a wonderful idea that comes from statistics by Roger Conker and Bassett from 1978. And the second one is from conformal prediction, which we'll see in a minute. So a naive way to think about the problem of actually constructing accurate prediction interval is to say, well, I don't know what are the conditions, the quantiles of my distribution, but I could try to fit them by all the great tools you use, by gradient boosting machines, by deep learning, and so on. And so how you would do this in practice, you would say, well, I can use my deep learning architecture, but instead of feeding a regression function, which is what people do usually, is I'm going to change the loss function to be what in the literature is sometimes cutely referred to as a pinball loss, which is something that looks like the absolute loss. And so, for example, if alpha were 0.5 here, you would get that the loss is just the absolute value, in which case people who know a little bit about statistics would recognize that you would actually fit the median. But by tweaking the slopes, this function is actually trying to estimate, this loss function will actually try to estimate the quantiles of the conditional distribution of y given x. So instead of using the squared loss, you use a pinball loss, and you use it for a value of alpha, it's say equal to 0.05. You use it for alpha equals 0.95. And so you get two fitted functions using modern methods, let's say neural network, why not? And then at the end of the day, you get what you think are estimated quantiles from empirical data. And you may actually get two curves that look like this. All right, would that work? Would this be valid prediction intervals for test point that you have not observed? And the answer is, well, no, it doesn't. And when I actually provided the method with a new test sample that the training set had not seen, obviously, I can see that the coverage is very far from 90%. In fact, it's 66%. And so for those of you who fit neural net as routinely, you should not be surprised with this. You know, a lot of times neural net will actually be trained to zero error, in which case maybe your quantiles will actually be, two quantile function will be extremely close to each other. And so you might not expect to see coverage on things you've not seen. And that's what you see. Okay, so yet what we're going to do is we're going to see how we can fix this. And we're going to add a wrapper around your predictive algorithm, your neural net, your gradient boosting, whatever you want, such that you're going to have perfect coverage on unseen data samples. And this, as you will see, will hold no matter what the dimensionality of your data set is, no matter the generating mechanism, no matter the fitting procedure you use. And so it's a foolproof layer. Okay, so how is this going to work? So the first thing you're going to do, and there are variations on this idea, but I prefer to introduce the simplest idea, is to take your data, the data you have, and split it into what we're going to call a training set, a proper training set, and a calibration set. All right, so I do a split, maybe 70% on the proper training set and 30% on the calibration set. And on the proper training set, I'm going to fit quantiles, just the way we've seen. But we've seen that it doesn't work, so I'm going to calibrate this, what I've learned on the proper training set, by looking at what happens on the calibration set. And here it's going to see how it's going to work. What we're going to do is we're going to take points in the calibration set and we're going to give them scores. And then we're going to look at these scores to adjust the predictive interval that was fitted naively. All right, so this is very, very simple to, conceptually very simple. And let's see how we're going to score calibration points. All right, so this is perhaps the part of the presentation that is, you see, this is not a very technical talk. This is maybe the most technical slide. I'm going to have calibration points on the right. And each calibration point is going to get a score. And it's going to get a positive score if the calibration point is outside of the predicted range, and a negative score if it's inside the predicted range. And the score is simply going to be the distance of this point to the nearest boundary. Okay, so for example, the score of this point is positive because it's outside, and the score is simply the distance to the upper quantile. And this point is inside, so it has a negative, and so it's going to be the negative distance to the lowest quantile because it's closest. And so each point gets scored in this way. And let's say I have a calibration set with, let's say, 300 points in the calibration set. I'm going to get 300 scores this way. 300 scores that I'm going to call SI. Okay? And so some of them are positive, some of them are negative. Okay? And so I have 300 scores. And let's say I want to construct a 90% predictive interval. Then the procedure is extremely simple now. I'm going to look at the 90th percentile of these 300 scores. So I'm going to look at the 270th largest value of these scores. Let's call it Q, right? So I'm going to call Q to be the percentile of these scores, the 90th percentile of this score. And what I'm going to do now is I'm going to look at my naive prediction interval, and I'm going to adjust it by this percentile Q. So I'm going to subtract Q to the lower quantile, and I'm going to add Q to the upper quantile. All right, so it's quite simple. And so let's see what this method is doing. So suppose that actually I was extremely lucky that, you know, maybe because I had an oracle, that somehow the quantiles that you gave me are actually correct. Then, well, what would be the percent, what would be this value Q? Well, you know, if the quantiles were correct, so 90% would sort of fall in between, 10% would fall outside, and therefore Q would be very close to 0, in which case I would not change this. On the other hand, suppose that you were undercovering, like you're too sure about yourself when you should not be, then in this case, you would have more points outside, and so Q will be positive, and then of course you would enlarge your prediction band. And conversely, if you were too conservative, what's interesting about this method is in the case where you were too conservative, that is, you do too good of a job in some sense, like your interval is too wide, it covers too many points, then Q would be negative and you would actually shrink your predictive interval. So you calibrate your predictive intervals this way, and then when we actually run it on a new test case, it's almost too good to be true. We target 90% and we get an actual coverage, which is 90.09. So it's, as I said, almost too good to be true. And well, that's not a surprise. It's not a surprise because there is a result that says that if you follow this procedure, and if you start with samples that are exchangeable, it's a weaker notion of just being IID, which is what everybody assumes in machine learning. You have that the guarantee I can give you is that you're going to cover with at least 1 minus alpha of the time, fraction of the time, and no more than 1 minus alpha plus something very small, which has to do with the size of the calibration set. And again, I want to emphasize what I said earlier, that I've made no assumption whatsoever. You can use any algorithm you want, any predictive engine you want, and this will work no matter the distribution of the data, no matter the sample size, and no matter nothing. So it will always be accurate. Now, this is a special case of a broad idea known as conformal inference. And here you see perhaps the intellectual leader of conformal inference. It's a field that developed around Vladimir Vogt, whose work has inspired me greatly over the last few years. So to build predictive intervals, Vogt had an idea of using conformal methods. Here we're proposing a different way of building predictive intervals. I think one of the problems we had with the Vogt method is that it tends to build predictive intervals. Well, it doesn't tend, it builds predictive intervals of fixed widths. And so here on the left, you have a data set with a lot of heteroscedasticity. As you can see, the uncertainty about y given x changes a lot as a function of x. And the method developed by Vogt is actually fitting a prediction interval that has the marginal coverage that I'm talking about, but has constant widths in the sense that the width does not adapt to the data distribution. What you see on the right instead is you see the method I advocate, where you can see that when you have heteroscedasticity, the method actually produces intervals of lengths that vary with where you are in covariate space, so that when you are pretty sure about the response, you get intervals of very short length. So what we can see from this very academic plot is that both methods achieve the coverage you want, but one is more informative because it has shorter average length with the other. And it's because the method I introduced is adaptive, while the original method of Vogt is not. Okay, so on the right here, we see the lengths on the previous example of this method that I present. And we can see that the length of your interval depend really very much on where you are in space, whether the length of the competing method doesn't. And even though the method cannot achieve conditional coverage, that is, we cannot say that given the value of x, you're correct 90% of the time. It's just over future samples that you're going to be correct 90% of the time. We can see empirically that when we look at coverage as a function of x, the blue curve is essentially the conditional coverage of the method I'm advocating, and it's far more consistent than this method, which can sometimes dips below dips high, dips below, dips high, because it lacks this adaptivity. So it produces shorter intervals, and it achieves, even though you cannot prove it, it's not possible to do so, it achieves a form of conditional coverage. So you can actually start to deploy this method on real data, and we have. And so here's an interesting data set where you're trying to predict healthcare system utilizations as measured by maybe perhaps the number of visits to a doctor's office or hospital. And you have a lot of features, which might be your age, your marital status, your race, which we're going to be talking about in a minute, functional limitations, health status, and so on. And so you might want to be able to predict how much healthcare you're going to need. And so when we actually look at this method over patients that we have not seen before, then we can see that this method, CQR, achieves a 90% target. We can see that conditionally on X, it also achieves very close to the target, whereas the competing methods do not. And not, as I've mentioned before, but now it's on real data, we can see that these intervals are far more informative because they're shorter than those given by competing methods. So you have a way to actually wrap around a predictive engine to actually give a confidence range that you can actually trust. And so we've actually looked at a lot of data sets coming from a lot of different disciplines. And so when we were looking at this method of conformalized quantile regression, we could see that it sort of outperforms competing methods in a lot of cases. But I don't really want to belabor this point too much. So it's a good method, and perhaps that's a method. That's the reason why the Washington Post wants to use it on Tuesday night to actually project election results with confidence. There are some variations on this, and maybe I will skip this. Variations include what to do when data is scarce. So, of course, here I'm going to split the data. One part is going to use to train the data and figure out the quantiles. The other will just calibrate the quantiles. It's actually possible to do something like cross-validation. It's more sophisticated than cross-validation, but it's possible to actually reuse data points so that they are both used for training and for calibration simultaneously. It's not trivial to do, but we have a method to do this, and this is work with Rina Barber, Aditya Ramdas, and Ryan Tibshirani. And so you can actually use data both to train and to calibrate. You just don't have to rely on data splitting. And so, of course, you're going to get shorter intervals because you ask your data to do more. And a second thing that I'm not going to have time to discuss very much is that we have also versions of this for labels that are not continuous but are discrete. And so, for example, suppose that I give you a response which takes on 10 possible values. Let's say the MNIST problem. You might want to design a system such that you can say you want to be sure that instead of just reporting your best guess, you might instead want to give me a short list of labels about which you're 90% sure that the true label lies. And we know how to do this, and there are variations of this, and we have a NeurIPS paper this year that explains how to adapt the methods that you've just seen to deal with discrete labels. And so you could put one and one together, and so now we have lots of tools. If you have discrete data, scarce data, that would actually return prediction intervals with the guarantee you want, and we'll try to be as efficient as possible. Okay, so this is a method to try to understand when we have data and we want to use this data to figure out how much we've learned from the experience of others. We can give prediction range that have a level of accuracy which is whatever you want, and this will work no matter the data generation mechanism. So now I would like to move to a second topic, which has to do with a very minimalist view on algorithmic fairness. And I want to explain how these ideas can be used to inform a bit some of the ideas that are floating around notions of algorithmic fairness. And so remember that we need to be extremely careful about what we do. I don't think I need to convince this audience that this is one of the most important problems we need to work on. Okay, so if you look at the example that I mentioned before, I mentioned that there's a very special attribute here, which is race, which is a protected attribute. And so we can look at what the method does when we group people according to race, being white or non-white. And so here we see that if I fit a neural net, I'm going to observe, and this is just an empirical observation, that the neural net that I fitted overestimates the response of the non-white group and underestimates the response of the white group. So it's a bit, in a way, biased against non-white, if you see what I'm saying. Like, of course, it's not enormous in this example, but you can imagine scenarios where you have a severe bias in the algorithm you use to actually make predictions about individuals. So this forced us to think a little bit about what should we do then. So when you want to learn from the experience of others, and at the same time you want to treat people equitably, what is it that you communicate to decision makers? If I'm a data scientist, I am not a decision maker. This is a point that I'm going to make later. I'm a data scientist. Decision makers are interested in learning what data tell me about the problem of interest. And so I'm going to use a very fancy model. Maybe it's a neural net. It's very hard to explain what it's doing. Maybe it's a gradient boosting machine. It's very hard to explain what it's doing. But how can I communicate the results of data analysis to people who will make decisions based on what I say and achieve two goals at the same time? One, I don't want to overstate what I've learned from the experience of others. And second, I want to make sure that I treat people equitably. So I really view, and I want to follow Corbett, Davis, and Goel in this, and I have a view on a minimalistic view of fairness in machine learning. First of all, I would not be able to define fairness. I think it's an ill-defined notion. And I think one of the things I see in algorithmic fairness in machine learning is people try to conflate the risk assessment problem with the policy problem. And for me, they're completely separate. There's a machine learning problem of evaluating risk. And then there's after you find the fact, what do you do with this as a policy? And so this goes somewhat against the current thinking in algorithmic fairness, and I would like to explain that. So the current algorithmic fairness is that basically you're going to write down a definition of what you think is fairness, and then you're going to try to create an algorithm that obeys this definition, and that might be a good thing to do in some cases. The problem is that people may have different notion of fairness, and it's been shown that these notion of fairness are not compatible. That is, you cannot write down an algorithm that would obey like what person A thinks is fair and what person B thinks is fair. It's just not possible. They're incompatible. So one notion that is quite discussed in algorithmic fairness would be this notion of equalized odds, that I'm sure that is actually one of the authors is from Berkeley, equalized odds. And equalized odds gets its insight from binary classification. And so here, you know, it's basically we have a label Y that can take on two values only. We're going to make a prediction that takes on two values only, 0 and 1. And what you're asking when you do equalized odds is you want that essentially the fraction of errors, like of course you can make two types of errors, you know, a type 1 error and a type 2 error. You have true positive and you have false positive and false negatives. And so you want that the false positive rate and the false negative rate be the same across groups. Okay, so a definition that looks like this. And this is a kind of the, when you formulate it, it seems something like that might be extremely desirable, except that it can lead to unintended consequences. And so formally, the definition asks that your prediction be independent of the protected attribute, conditional on the response. But there might be intended consequence. So maybe I have a bunch of slides about intended consequence, but I don't want to take too much of your time in this lecture, so I'll mention just one unintended consequence of equalized odds, and this is this, which is that because you want to equalize your error rates, well, one group might be easier to learn than another. So for example, it might be easier to learn the outcome for the majority group, let's say for men, than it is to learn the outcome from a female. But because you insist that the two error rates must be the same, basically the algorithm is going to have to flip its prediction for people about which you're pretty sure about the outcome, but you're going to have to flip this prediction to make sure that the two rates are actually equalized. And so you end up in this very strange situation where you're pretty sure that the response of an individual is this, but you're going to have to flip it just because the error rate has to match the error rate of a group about which you're less sure. And so this is very strange, right? Basically, you're acting like a decision maker. You know an outcome, but you're not going to report the outcome because something that you are baking in prevents you from doing this. And I find this very, very strange, to say the least. And so it's important that we empower the user. We don't want to play God. We're not decision makers. We want to present the decision makers with facts. What is it that I have learned from the experience of others in a way that treats people equitably? And so this is where we thought that we could actually use this principle of trying to report prediction intervals. And so we have a notion called equalized coverage. And equalized coverage would say something like this. I have data about individuals. Let's say I have a majority group males and I have a minority group that are females. And my goal is going to be for each new person, I want to report a predicted range based on what I've learned from data in such a way that the range is correct no matter what protected attribute you have, no matter what group you belong to. And so the prescription that we have, which is a very minimalist view on algorithmic fairness, is to say this. I have a new person with attribute X. You asked me to predict Y. Here is a predicted range that is unbiased, that holds 90% of the time, and holds regardless of group membership. And I think when you approach things this way, you have a tool which summarizes what you've learned from the experience of others, rigorously quantify uncertainty, right? If the interval is large, so be it, that's what you've learned, and you don't pretend that you know more than what you do. Don't reify the prediction. This is what you have to deal with. And it's treating everybody equitably because you have the same prescription no matter what group you belong to. And what we find when we run application is that sometimes for a group, the intervals would be wider. Why? Because they might be harder to predict. Also because maybe I have less data. For example, if we look at biology applications, we have a lot of data about men, but we don't have so many data about female. And so what we find typically is that ranges for female are wider. And so it tells the decision maker that it's about time that you collect data about females. So now suppose that's a prescription, how would I do it? Well, I have my minority group, I have my majority group, and here they are. And I can split them, I can separate them from the get-go, but that would not be very interesting. What I would do instead is, in the training stage, I would pull everyone together so that I can learn from the experience of everyone. But then when I calibrate, this is where I separate them to make sure that my calibration is valid, conditioned on whether you belong to the majority or the minority group. And if you follow this procedure, then you'll have exactly the kind of interval that have the prescription I've talked about. So this is a method that is highly operational, right? I make no assumption of any kind. I can use any machine learning algorithm I want to learn the response Y. And so again, when you use CQR and we train jointly, then what you can see is that, well, you get exactly the coverage you want, so you fulfill your prescription. And so this is kind of what I wanted to say. And I think, you know, just to look at a bit of data ethics, you know, when you analyze data, it's non-neutral. It's very important to me and to my coworkers to be able to report the result of data analysis in a neutral way. And again, I don't want to conflate the decision-making with the job of a data scientist, which is to actually tell decision makers what are the facts. And so I think Corbett Davis and Goel said it very nicely when they said that a machine learning algorithm can predict correctly that, I don't know, the chance of recidivism is 20%, but that does not determine a course of an action in and on itself. The policy is separate from the fact finding. And what we advocate here is to keep them separate. Finally, I was very interested in preparation for this lecture. I'm actually reading quite a bit, not from people well, I've read their papers, people who work on algorithmic fairness in machine learning, but I'm starting to read from actually legal scholars themselves. And so what I'm reading is quite interesting because, you know, as I said, fairness, even from the point of view of the law, is a very vague notion. There's, you know, not a real consensus about what that is. So people do not agree on principles. So if people do not agree on principles, it's going to be very hard to encode it into an algorithm, right? And so people see that there will be a clash between the law and the literature on algorithm fairness very soon because of this. And so I think we need to think about algorithms in minimal terms. And again, what does the data tell me? And I presented a way of telling you about this. Okay, so Shankar, I've not gotten to conformal inference just yet. I'm going to ask for guidance about how to proceed. Maybe I can stop here. I talked about prediction intervals.
Really, just a little bit on
just a little bit, and then okay. All right. So let me just go a little bit on counterfactual inference. So with an eye to counterfactual inference, so here is a major problem in statistics and in life in general, I would say. You have individuals and they are either assigned to a treatment or a control. And so you might even say, toss a biased coin to actually assign your individuals to either a treated unit or a control unit, according to what people call in the field a propensity score. And the basic question is this, which is that you have observed data, right? You have a counterfactual, and the counterfactual is, let's look at this individual. This individual was assigned a treatment. So this individual has two potential outcomes: the response to treatment, the response to placebo, but you can only observe one of them. You can, of course, not observe both. And so what we have here is what Don Rubin calls a data science table, where I would like to see for the same individual, the counterfactual, but I don't get to see it. Okay, so we have two potential outcomes, but we can only see one. And so the question we're going to ask is, can we actually make an educated guess about the counterfactual? So let's take this blue individual. This blue individual was untreated. And what we're going to ask now is, what can you tell me about this individual, the response had this individual been treated? And what can you tell me with the prescription that we've seen before? That is, are you able to produce a range for the potential, the missing value that you have here that holds, that is correct 90% of the time? Okay, so how do I infer? Let's say in this individual, I saw Y0, I did not see Y1. How do I infer Y1 from the data I have? And so we are in a setting which is more challenging than we've seen before, because now the individuals have been selected to belong to a treatment or a control unit based on the value of the features themselves. So you see, what I'm trying to do is I'm trying to do something which is quite delicate here. Let's say I'm going to try to predict the value of a response to treatment of a person who had actually not been treated. So fundamentally, I'm asking a question about this distribution. What would be Y1 given X, given that X has been not treated, that is, given that I have a sample from X, given that T equals 0. And I want to find out something about the response Y1 given X, but for that, I only have individuals like this. And there's a covariate shift, right? The individuals, the examples I have, which are over here, which tell me something about the response to treatment, come from a distribution that have a different distribution of the X's. And so I have what is called a covariate shift. I have a mismatch between the training data, the data I have to learn, and the population about which I wish inference that follows a different distribution. And so in other words, this is something like this. I live in the real world. I have treated units. And here I have the distribution of the X's. So maybe what we can see from the bottom left plot is people are treated because they have a low value of X. All right. And these are the values of Y1 for the people that have been treated. But now, I want to know a counterfactual. I want to know a person who did not get treated. So this person has a high value of X, likely. I would like to know his or her response to treatment. And so we can see that the counterfactual world, because these two base distributions are not the same, I don't have samples from the counterfactual distribution. I just don't have this. And I need to deal with this. Okay, so this is a tricky question. And really, if you try to lay it bare in very simple terms, is you have IID sample from a distribution which has a distribution of the features X, and you have a distribution of the response given X. But, okay, this is what you can learn from. This is the data you have at your disposal. But what you learn from is you want to actually make prediction about a different population. And this population is different in the sense that it has the same conditional response of Y given X, but the base, the distribution of the features X is different. All right. And so in particular, you have sort of the covariate shift ratio, which is essentially the likelihood between the distribution under the target versus the distribution under for which you have data. Okay, and so now we need to learn how to make prediction when the distribution is changing, and it's changing how the distribution of the covariates has changed between training and testing. All right, and what I'll say is, I'll just say this, I'll say that it's possible to adapt the ideas of conformal prediction to actually do to this new world. And so in a 1 minute, because I just want to close now, in 1 minute I'd say, well, you're going to compute your conformity scores the way I presented before. And so these are the conformity scores that you would get. But because now you're actually changing the target distribution, when you're going to compute the quantiles of your conformity scores, these distances that I mentioned before, you're going to reweight them. And you're going to reweight them by precisely the likelihood ratio between the target distribution and the training distribution, the test distribution and the training distribution. And so what you do now is you're going to reweight your conformity scores, and now you're going to take the quantiles of a new empirical distribution that has the same mass, but they are weighted such that training points that conform more to the testing distribution are weighted more than training points that conform less to the test distribution. So you're going to upweight certain conformity scores and you're going to downweight certain conformity scores. And when you do something like this, when you do these reweighting cleverly, according to the covariate shift between testing and training, you can show that you're going to get exactly the same guarantees that you have. And so now I can make a counterfactual claim. And so if I'm in a scenario where I'm going to assign people at random to treatment or control based on some propensity score, E of X, then if I follow this reweighting procedure and I follow the principle of this conformalized quantile regression, then what I can do is I can construct a counterfactual interval for the things I have not seen and I would have liked to see that has the right coverage. That is, it covers 90% of the time plus something negligible. And so I can actually give you a very precise range for the values that you did not get to see. And so what we can see is we can push these ideas very far and actually provide counterfactual inference for things that, yeah, okay. So I'm a bit short on time, so I'm going to skip all of this and just say in conclusion that we have codes, so everything we talk about can be downloaded and you can reproduce the figures in the spirit of reproducible research. I'm very happy to entertain questions. I'm sorry that I was a bit long, but it's been a great pleasure for me to speak, Shankar, and I hope that you continue doing well with your great institute.
Fantastic. What a tour de force, Emmanuel. There are a couple of questions, so let's at least try to get to them. So the first by Eric Majumdar, a great talk. You mentioned that you make no assumptions on the underlying algorithm generating, this is the first part of the talk, generating the empirical quantiles. But is there an implicit assumption that the problem can be solved to zero training error on the training set? That's the question.
Yeah, I mean, you could do that, but then the problem is, so suppose, yeah, that's a good question. So you make no, so the power of this method is you make no assumption anywhere. Now the thing is, if you use an algorithm which is not good, right? So for example, suppose that you have zero training error. Let me just be a bit quick here. You make zero training error, so your two quantiles are the same, right? So then now you go to the next phase. And the next phase, what do you see? The next phase is this, right? The next phase is this. So now your two quantile functions are the same. Everybody gets a positive weight. So now what will be your predictive range? It's just going to be the quantiles of the y value itself. So you're going to return a fixed interval of fixed widths. It's always the same interval, no matter what x is. And so it's not informative. So you want to use a good algorithm to get short intervals. The method will always be valid. You will always get 90% coverage. But it's only if you use a good method that you will get short width. Otherwise, you might get very uninformative intervals.
Fantastic. One more question, Olivier Massicot. Thank you for the talk. The theme of this talk is about closing the loop. So he says, the policy problem is separated from the prediction problem, but it seems we close the loop by providing predictions to decision makers. And the question is, when they take decisions, how does it lead to biased feedback loops? That's the question.
But I think what I'm trying to argue is, so thanks a lot for the question, which is a very good question. I think what I'm trying to argue is I do not want to provide a decision. That's not, you see, what I don't understand about the current status of algorithmic fairness is I don't want to give me you to give me a prediction y hat. You know, I don't think we should use an algorithm that says, yes, this defendant will commit another crime. What I want to learn to tell is like, what is it that I've learned about the problem? So I want to give a range of prediction, which is, I don't want to make a decision. I want to tell the decision maker, the goal was to use data to understand the future. What have we learned from data? And so I don't want to make a decision. I just want to say, based on previous applicants and students enrolled at Stanford, my predicted range for this particular applicant is this. And it's constructed in such a way that I'm 90% correct, no matter what group she belongs to, no matter whether she's white or not white, no matter whether this is a male applicant or female. I don't want to give you a decision. My goal is to shy away from decision. That's why I call the approach extremely minimalistic. I want to give you a sense of what I've learned from the experience of others. I want to give you to do uncertainty quantification. I want to give you a range, and I wanted to do it in an unbiased way. That is, my range is not always correct for, let's say, white, and never correct for non-whites. But I don't want to make decisions because they're separate, I think. If we can solve the machine learning problem to infinite precision, we still have a policy problem.
Yeah. Fantastic. Emmanuel, that is a fantastic talk and a fantastic methods. And needless to say, as I watch the election results on Tuesday next week, I will remember that your algorithm is driving the Washington Post predictions. So I will
exactly. So,
attribute greater weight to them. So
yeah. So if you want to get your facts straight, I would say go to the Washington Post. And the way it's used is that the algorithm is going to be turned on. So again, this is the work of John Cherian and Laney Bronner. Some counties will start reporting, and then the algorithm will actually make some prediction about the missing counties.
Huh. Fantastic, fantastic. Well, that's wonderful that you got this sort of really recent results out into trial, so quickly. That's fantastic. By the way, the methodology also just fantastic. It's a real tour de force. Congratulations. This is just
Thank
great.
you very much, and thanks for having me, and thanks for tuning in.
Thank you. All right. Thank you very much. So with that, I think before we lose everybody, I will say thank you to Emmanuel. Thank you. Okay. Bye-bye.
Bye-bye.